Okay, welcome back everyone. How's everybody doing? So we have a new topic. We'll talk about functions of many variables today and calculus of functions of many variables. But before we do, I just wanted to check if there are any questions. And so the quiz results should appear soon. I see that, yes. So we are starting section 14. So chapter 14, and it's section 14.1. I just started with Mathematica. I just wanted to show you some pretty pictures before we switch to the note-taking app when we'll do some calculus. Right. So yeah, so what's a function? So we'll now look at functions, the function f of x. So before we had function of single variable, which was you have some expression, for example, x squared plus 3x plus 2, right? That was a function of one variable. And now sort of the idea is, or another example, so g of x is equal to exponential of x minus 10. So we studied a lot of these functions, in particular differentiable functions or continuous functions. And now we'll go one step further. We'll add more variables, right? So consider expression which depends now on two variables, right? For example, it's sine xy, or x multiplied by y plus xy. Well, so what is this thing, right? So you have a same way as with function of one variable, we have a domain. So this function f, it maps. It's a, let's say there's a set D, which is a domain, and it will be a subset of, in our considerations, n-dimensional Euclidean space, right? And then we send it to R, right, to the real line, right? So that's a real valued function, right? So a point with coordinates x1 and so on, xn will go to the value of the function f of x1 through xn. So D here is called domain, same terminology. This R is codomain. And the rest of the terms that come along with this situation, they also apply, right? So the range, right? So range is set of, range f is a set of all values. It's a subset of, yes, sorry. It's a subset of a domain. So it's a set of all y inside R such that f of x1 and so on xn is equal to y for all x1, xn from D. right? So you simply take all the, look at all possible values that the function takes, that will be the range, right? And then we say that the function is onto if the range coincides with R. Now that's right. And we say that it's one-to-one when for every value of R, there is only a single value of the tuple x1 through xn, for which this value is equal to f of x1 through xn. But you can imagine that just from the dimensional grounds, this is highly unlikely, right? So it's very hard to come up with a function which is one-to-one, right? And so from the perspective of linear algebra, of course, we know if it's a linear function that it's only one-to-one if the dimension of domain and codomain are the same. So it's almost never one-to-one. Okay, good. So well, we can draw some examples here. So we can draw a graph, which is a three-dimensional plot, right? So it's a set of points now in three-dimensional space, such that the x-coordinate is, it's the function, this f of xy, which is plotted relative to to x and y. Here's the plot for sine x plus y squared. Well, let's put this function. Let's see how this looks like. Well, I think we need to go a little bit further. It's like sort of sine xy. Sine xy is a doubly periodic function, right? It has, well, we can extend the range a little bit. Right, so the basically, if you pick a constant value of y, right? So for example, if you pick y is equal to 0, then you can look at this plot like that. Then there'll be a line. I'm going to try to draw it. So there'll be a line which goes through the origin, right? Like this line here, and then it's on the other side. It's the x-axis, right? And same true with the y-axis, because the function is identically 0. And otherwise, for every 3p, what's that? Yeah, so and otherwise you have a periodic function which looks like sine of x or sine of y at any section. You can make a section here with a plane, and then it will look like a piece of a sine function. The graph is 3p. No, actually not 3p. I mean, you don't see well, you don't see the. Okay, maybe I can make it a bit bigger. So, okay. Oh, confusing. Okay, so. Okay, let's start with something easy. But cool as well. Okay, so this is sine x, right? And now it looks like a tinfoil folded in the shape of a sine function, or like a wave in the ocean in a perfectly straightened beach. Like so, in the Bay Area, probably Stinson Beach is the closest one. Right? It's one of our favorite. Yeah, so you see how the waves would do that kind of pattern. So here, it's a function of two variables, but it does not explicitly depend on y, right? So that's why every section, every section like this would just give you the profile of a sine function. I hope kind of cool and strange. Well, I mean, okay, so this is the world of multivariable functions. We're doing multivariable calculus. Get along with that. Right? So, let's see, maybe I can make a cooler color. So let's do, maybe you don't like orange. not trash red. Too dark. Is that better? Okay, well, we're gonna switch colors just for the contrast. Never mind. Anyhow, so and now let's make it a little bit more interesting. Let's move it to let's add sign of x plus y. Right. So, that's what you get. So now, well, you essentially have the wave, but only now this wave, well, propagates. If you want physics terminology, it moves in the x plus y direction. It's okay. Yeah, so sort of it moves into x plus y direction here. Of course, you can, you know, it doesn't look much different from what we had before because it's the just rotation of the picture by 45 degrees. But the picture that we had with the product, see, like if you look at this from the top, it looks even more interesting. So you have basically this hyperbole, right? This shape. Right. So the well, we'll get to this thing in a second. But basically, right. So what we had in what we talked about before, this line here and this line, they are the coordinate axes, right? So the x and y, and then in between them, well, there's some sort of oscillation going on, right? And if you look at this from the top, right? So then you would look. It looks like a family of hyperbole, sort of with imposed oscillations on top of them, right? Because it's a sine function, and then basically it's a product of x, y, right? So when you have a hyperbole, it means that x times y is equal to constant, and then that constant changes, right? Because the sign oscillates. Okay. Let's look at some other examples. Of course, I invite you to play with this thing at home. Right, so then let's take for example, well, let's go to logs, right? So let's talk about something with more interesting domain. Maybe first let's do square root. Square root of, I don't know, 1 plus x plus 2y divided by x squared plus y squared. Okay. That's weird, right? Oh. Okay. So see here, it looks like a volcano, right? Only cut by this line, right? So the reason why there's a it's not defined everywhere is because there's a square root, right? So it's if you're looking at real variables, what's then under the square root should be positive, right, or non-negative. So then you can see it's positive beyond this line, which is given by that equation. And then the reason why there's this kind of cutoff, like there's a spike here, right, is because there's a singularity at the origin of the coordinate system, right? So as x and y approach 0, this becomes a constant here, right? And the denominator goes to infinity. So the graph goes to infinity, and then the plot here just cuts it off. Right? And then there's some smooth decay, smooth decay elsewhere. So the domain of this function will be right? It's the set of x and y inside R2, and for which the 1 plus x plus 2y is greater or equal than 0. And what is the range of this function in that case? Yep, that's right. The range is from 0 to infinity. Yep. Okay. And now let's look at a bit log. Let's look at log of can you explain how we would find the domain and range of these multivariable functions? Well, sure. Yeah. So I want to just show some examples first, and then I hope it will be clear after those. Yes. Yeah. Oh, the z coordinate. Yeah, I said it in words, but maybe I should say it. So the z coordinate here is so it's a 3D plot, right, with x, y, and the z coordinate is f of x, y. Right. Yeah, so it kind of goes without saying. Yeah, that's right. So when you study, for example, a function of 3 coordinates and more, it's becoming impossible to depict it in, well, 3 dimensions. You're going to have to use your imagination for that and algebra. Probably should make it a bit bigger. Okay, so now let's take log. Y, we multiply by x. Huh. That's pretty. Oh, that's pretty. So, Shayla, can I use your adjective now? Trippy. Does that look trippy? Well, the reason here is that it's well looks that there's this. Well, I mean, you can increase the calculation precision, but basically this kind of chainsaw kind of pattern is just a computer error. I mean, you can calculate it a bit better, but basically you can see here, if you look at this plot from above, right, like this, there's a parabola here, right, which is of course given by the equation y equals x squared. So there was a question from Sarah about the domain and range, right? So, so Sarah, what's the domain of this function? You can probably tell me by looking at the picture and by on the formula. Or anybody else is welcome to answer. So, yeah, everything is real. That's right. So, so basically, domain is defined by. So think about it this way: that all values of x and y are possible unless something goes wrong, right? So, what can go wrong with the log? Yeah, that's right. So, yeah, so x squared minus y should be bigger than 0, or the other way around, right? So y is less than x squared. So what stands under yeah, that's right. So what stands under the log function? So this sorry. So the x squared minus y should be bigger than 0. Ah, you answered what could go wrong. Okay, of course, yeah. So, which means that y is greater than x squared, which is of course all this orange thing here. So here, if you draw this, if you look at the xy plot, this is the plot of the function y equals x squared, and we are looking at everything that lies under it, right, under this parabola. Yeah. So that's this is the range. Yeah, range of the function is set of all values of x and y such that y squared is bigger than x squared. And what is the domain? So for that we need to rotate this a little bit. So you see you have x multiplied by this function, right? So I'm a bit more concerned about the Tyrian effect. Well, I mean, so I mean this chainsaw kind of thing. So it's not real. It's if you should sort of artifact of the computer. I can increase the tolerance. So where is this? Or you calculate the domain, and I'll try to find it out. So basically, okay, there's a way to make it more beautiful. You can increase precision of calculation, and then it will make it work. Yeah, let me fix it back next time. Anyhow, so what's the range? So how would you find range, right? We just look at all possible values that this function takes, right? So log clearly is only positive and grows from 0 to infinity, values of the log. And then x can be any value, right? So that's right. So it should be all real numbers. So there's nothing wrong about 0. See, like 0 is somewhere, it's somewhere here. So the so it does because it's a range, right? So Clarice, you don't have to put 0 in the expression to find value zeros. For example, when the argument of the logarithm is not 0, but x is, the value is still 0. So yeah, so here range is the whole set of all real line. Okay, so let's look at a couple of more. Well, I guess this one you should be able to tell me right away. What that will be. Or rather, should I do, I'm sorry, 1 over 25, right? So if I draw that, what will be, what this function shows? Any guesses? So remember, that should be equal to f of xy, which is z. Well, ellipsoid would be if it's, so first of all, it's a half only, right? Because so if usually it's only the top branch, where here there's a plus sign, right? So it's a dome, right? It's a dome of the sphere, right? So there's a hole here. Right? It's a hemisphere. It's a northern hemisphere. And so yeah. Does that make sense? Yeah. So of radius 5. We can put a minus sign. that will be the lower, the southern hemisphere. So if you, so these are two branches of this function. Z is equal to square root of that. So because it's a function, right? And then we typically, when we say function in real analysis, we mean single valued function. We can only capture one branch. Okay. Beyblade Stadium. Yeah. Okay, so I didn't expect it would be so much fun. Okay, there's some. Okay, let's. Okay, so that's how it works. So you draw these three-dimensional plots where the z-axis is played the role by the function itself. Yeah, and then often it helps to understand what the function does. Right? At least find its domain and range, and well, qualitatively see what's going on here. So. So okay, so the next part is next part of the story are so-called level lines. So now, okay, let's pick some other function. I think before I go, I want to show you one of my favorite, one of my all-time favorite, which color I haven't used yet. My yellow is good. Let's try this one. So so there's what's known as complex logarithm. So if you just like an appetizer for your complex analysis class. So if you draw the real, actually let's do imaginary. So if you draw imaginary part of the log function, you're going to get something that is really trippy, I think, right? So so that looks like a step of the staircase, right? So let me first explain what the function is, right? So here, well, you probably heard of complex numbers, right? So it's a pair of numbers x and y, so that there's number z, which is x plus iy, such that I squared is equal to -1. And then there's every complex number has real part and imaginary part. And then the real and imaginary part can be identified with a point in the coordinate plane. So you can calculate the imaginary part of the log. Well, it will be basically this function. So there's a the problem here is that so the way the imaginary part of the log is defined is that so if you have any logarithm of a complex number z, the way you define it is as such: it will be the log of the absolute value of z plus what is known as the argument of z, right? An argument of z is just its angle of this corresponding to this number in polar coordinates. So if you have, if this is your point z with so like z has coordinates x and y, then so this angle is theta, and it's called the argument of z, right? And argument changes between 0 and when you're along the x-axis to the 2 pi, right? So it's a periodic function like this. Now, with the log, what happens is that as you go around here, so as you go around the origin, right? So if you start say here and you go around and come back again, the function is not continuous anymore because the argument of z changes by a factor of 2 pi, right? So in complex analysis, you can every complex number you can write as absolute value of z times exponential to the I times theta. Have you probably seen this formula before? So for example, e to the I theta, you can write as cosine theta plus I times sine theta, right? So raise your hand if you've seen this formula before, or say something. Yeah, so Sarah's raising her hand. Yes, good. Thank you. Thank you. Right. So basically, to prove it, you just use the Taylor formula, Taylor expansion of the exponential. Right. You collect even terms in cosine and odd terms in sine. And the meaning of this is that if you look at the unit circle, right, in the on this complex plane, then every point here you can write as this, right? So it's a point whose, if it's e to the I theta, it's a point whose x value is equal to cosine theta and y value is equal to sine theta. So yeah, that's the meaning of it. Okay, so now, and this is true for every complex number, only that if it does not lie on the unit circle, you need to multiply by the absolute value. So it will be straight. Now let's take the log of this, right? So you take log z. Well, you need to define a complex log, but assume that we did. And then, so log of the product is equal to a sum of logs. No exception here. So it's equal to log of absolute value of z plus I theta. And here's where this discontinuity, this gap comes in, right? So it's because here, if you start with theta equals 0, and then as we complete the circle, theta becomes equal to 2 pi. And that's why you have the gap. So that's a famous discontinuity of the log function. And in fact, if you wanted to make the log continuous, you'll need to take another copy of this shape, and then you'll need to glue it on top of the glue it on top of the. So you would draw another thing, another sheet like this, and then you would kind of attach it to here. So it will go like this on another step of the spiral. So that helix that we beat it to death last week will appear here again. So you'll go on a spiral staircase up or down indefinitely. Yeah, that's the goal too. Yeah, or you can water slide down. Yeah, that's right. But you will keep falling all the way to infinity, right? So because the argument changes, theta can take any value. Okay, but since this, I think it's worth mentioning. I should not lose the opportunity to talk about this different branches, right? So let's just take square root, right? So square root of x plus gonna do iy here. How should we do it? Yeah, so say let's take real. Which color? Haven't tried yet. Which in the book? So the yellow, orange, and blue. There's no indigo. Well, let's just use the standard. Yeah, so say. Well, we had green before, but maybe there's a different green. What's the full colors? Light green. Let's take light green. That's not light green. Okay, we have to get to the imaginary part. So that's the same thing, only with a different function, which is the square root of z, right? So again, so there's this discontinuity here because there are two branches, right? There's a plus square root and minus square root, and now if you plot them together, another one we'll plot with the minus sign, and we change the color to, I don't know, like that, right? So we see here the here, this light green was the positive branch of the root, and this other color, which looks more yellowish, is the negative branch. So when you glue them together, you have this beautiful picture where, like, so that thing here looks like a parabola, right? Oh, why are they getting smaller? Right. Yeah, there it goes. So see, this white thing here looks like a parabola, and then these two branches sort of meet together along the negative x-axis, and then here they just go one for another. What's happening at the point in the middle where they meet? Well, yeah, so this is a singular point. This is so-called branching point, right? It's when you, so the analog of this point would look like, so if you try to draw the parabola x equals y squared, right? So it would look like this, right? And then if you try a vertical test, so every time a vertical line passes through the graph, it intersects it with over 2 points, except the y-axis, right? So here it intersects at 1 point. So this is called the branching point, right? And the same happens in complex world, only here, because the sheets are two-dimensional, right? They look like part of the real function. This branching point is actually just like a point, well, in some two-dimensional sheet. So the function is not differentiable here. We'll talk about this more in a moment. If you try to calculate the derivative of the function in this neighborhood, it's not going to exist, right? It's some singular point of the, well, no, it's not wormhole yet. So to do wormhole, you need to, well, wormhole would look something like this, right? So it's the, you know, and then you need to connect it with another one, right? So the, sorry, another way around. Yeah, that would look like a wormhole. You can fly through it. Anyhow, yeah. So I hope it was fun. So yeah, I encourage you to, when you'll do the homework, which I should send out today, to have some fun with plots. Okay. Good. So that brings us to level lines. Next part is that, so the level line is exactly what it sounds like. In fact, you know what it is. So if you look at the map, you know, the paper map on a computer, in some mountainous region, you will see level lines which show you the elevation or depth in the oceans. So let's take an example of maybe it's another famous function. Oh dear, why is it so bad in the? Okay, let's change range. The better plot range. Yeah, that's better. Okay, so this is the probably have seen this function before. It's the Gaussian, and every slice, if you make a slice through either x equals constant plane, or along the x plane, along the x-axis or the y-axis, you will have you have a Gaussian, so here it looks like, you know, let's make it a bit smaller. Right, so this is a mountain, right? And then you can, well, just measure the value of the function, right? So say you know, this is the function, you know, it goes f of x comma y, and then you want to study the set of points such that f of x comma y is equal to, say, constant c, omega for h for height, right? So say, so here, the range of this function in this example is from 0 to 1, right? Because it's an exponential. So when x and y become large, it goes to 0, and near the origin, the value of the function is around around 1. And so range of f is, well, 0 is never reached, so it's the open interval, but 1 is reached, right? So that's the range. So if you take the value of little h between 0 and 1, say 0.7, you'll get in this case, a circle like that. Right? And then, of course, you can kind of think of your mountain to be cut by this kind of level lines. Right? So, so a level line is a set of points. It's the set of x, y inside the domain, right? Such that so it's a level line corresponding to value h. Okay. So we'll look at all possible values of x, y, which live in the domain. Well, in this particular example, the domain is the entire plane, right? All values of x and y. Okay. Right, so it's we can look at some more examples, but perhaps we should start doing the calculus. Are there any questions? Okay. Great. So that's that. Now let's talk more about let's talk about limits, right? Limits and continuity. Okay, so we'll switch more to the note taken out the second half, but I think we can using the plots that we already have. It's can illustrate illustrate the notion of limits and continuity for multivariable functions, and you can see already that so based on examples that we got, that it's much more interesting than in function of one variable, right? Because well, so here clearly this shape over here is smooth and continuous, right? So how would you define continuity, right? So so first you need to define the limit of the function. So you would say that function is continuous if limit of f x y, so it's the limit of x y as x y goes to, so we need to explain a couple of things here. Some point AV, right, is equal to f of AB. Now, already this arrow needs explanation in a function of many variables, right? Because the when you live in 2 dimensions, right, it's not clear how would you go to some point, right? So we would say, okay, here's the point somewhere. That's my point AB. Green is probably not good. A bit bigger. And then what you want to do, you need to approach this point from, well, some direction, right? So you can approach it from here, you can approach it from here, from there, from there, from there. How did you choose which direction you would go? There is no good answer to this question, so that's why we define the limit that it should work for any direction, right? So in other words, you should take a small neighborhood, which is like a sort of small open disk that contains this point, right? And then if you pick any path, right, like those red arrows that show it, so if you go along any path, and then the value of the function, the value of this limit is equal to f of id, then we say that the function is continuous. Right, so it goes without saying in the function of one variable, because you have just no graph of a function and then just approach a point from one direction or from another direction. So yeah, what may happen, the worst thing that may happen in one dimension is that, you know, when you have a function which is discontinuous, it goes like this. It approaches one limit from one side and then approaches the other limit from the other side. So what we say in this case that the function is discontinuous, because, you know, in one dimension there are only 2 ways. There's left and there's right. In 2 dimensions there are infinitely many ways. So you have to take into account them both, them all. Excuse me. Okay. Questions? So we can write a formal definition in terms of epsilon and delta. So I'm going to shift it down a little bit. So let's give it in terms of the function of, well, we can have it in terms of function of many variables. The definition of the limit, right, is that, so let f be a function of many variables, right? So it's f a function from some domain, which is a subset of Rn to R, right? Then the so limit of f of x1 through xn as so then you can define vector x be vector of x1 through xn, and then vector say a will be a1 through an. This limit as vector x approaches vector a, and then we say it is equal to L if for every epsilon bigger than 0, there exists corresponding delta bigger than 0, such that for every vector x, so for every vector x inside inside the small disk that I drew inside the small neighborhood, so what we read is for every x such that the distance from x to a is less than delta, we have that the f of x minus f of a is less than epsilon. And so this is the formal definition. You can relate to well, it's a sort of direct generalization of the definition of the function of the one variable. No, we're not going to do much proofs now. So this week we'll go through chapter 14, all of its sections, if you have enough time. Yes. Let me illustrate this again in terms of this picture, right? So this distance here, but I encourage you to sort of to follow here. It's not really too complicated. So what does this fact mean? What does this equation mean? It means that square root of x1 minus a1 squared plus and so on plus xn minus an squared, right? That's the distance. It's the distance between 2 points. So if you pick a point x, so there's a vector. Here it's a two-dimensional example, right? So there are only 2 points. Actually, let's write them as 2. So it's a square root of x1 minus a1 squared plus x2 minus a2 squared. So that thing should be less than delta, right? So which means that there's a circle of radius delta, so that if the vector x, if the point x lies inside the circle, such that the distance, right, such that this distance is less than delta, this distance should be less than delta, it would follow that the value of the function at x minus the value of the function at a should be less than epsilon. Okay. And now the function is continuous if this guy, right, this L is equal to f of AB. So the reason why I spent so much time on examples, I think it was just to illustrate this notion. So let's sort of, after having said this definition, let's look at the examples above and just illustrate where the function is continuous, where it's not continuous. Okay, I'm going to remove it for now. So here, the bell, right, is continuous everywhere, right? Well, you can check it with the formula, but it's more or less clear. Okay, so these wormholes, they look a bit creepy, but yeah, so this is also continuous for all values of x and y. Now this function, okay, let me remove only one part, like this. So it's continuous everywhere except on the except here, which is the negative x-axis. Continuous everywhere. Except on minus infinity to 0, including 0. Like at this branching point, it's also discontinuous. Simply, you cannot go like this, right? So yeah, the idea of continuity is the same as in one dimension. Just you have, you should be able to walk on the surface without sort of any interruptions, without you should be able to smoothly slide. And here clearly this is not possible. And so as you approach on this side, there's a gap before you can jump on the next one, the other side. Okay. Same here with the log function, right? So it's continuous everywhere except the negative x-axis. So you would be able to you cannot. There's a gap here. This function is obviously continuous this function is, well, it's continuous on the domain of the definition, right? So it's continuous on every, yeah, on this open set, it's continuous. Right? So open set would be the y is less than x squared. Yeah, this function is also continuous on the domain of definition. So here, the domain would be, well, 1 plus x plus 2y bigger than 0, and x not equal to 0. Right. So in this open set, again, the function is continuous. And this guy is obviously continuous too, right? Everywhere. Okay. More questions? So yeah, perhaps maybe the, I think there's one another interesting example we can look at is this. Yeah. So then so the here, right? So that's an example of a function which is not continuous. So let me give you another one. So say take this quite famous. It's the 3D plot. Now, it may happen that the limits along different paths, along different trajectories exist, but they're different. So here's an example. There you go. So now let's do. There you go. So here, see, what happens here is that the, well, you can see it for yourself. There's something interesting going on at the origin, right? So as you approach, see here, when x is equal to y, right? Then so when x is equal to y, we have x squared in the numerator and 2x squared in the denominator. So this way the fraction becomes a constant. And that's why you kind of look at this from the top, right? You can see that the line here, when x is equal to y, one second, I'll answer the question in a moment. So this is the line x equals y. And when x equals to y, this function f of say x comma x, right, is equal to 1/2. And you can see here 1/2 is the value, right? So it's just this line that looks at 45 degrees in the x angle. But if x is not equals to y, right? So then sort of as you kind of move away from this locus when x is equals to y, as you approach 0, right? The denominator, so the denominator decreases faster, right? So, for example, how about x equals to yeah, and then we're good. So no. Now let's speak what happens when x equals to minus y. So x equals to minus y will be this kind of line here, and then it will re-emerge on the other side. So when x equals to minus y, so f of x comma minus x is equal to minus 1/2. Right? So And now somehow what you need to do, you need to, well, here are these two lines, x equals y, x equals to minus y, and you think of it that you need to, well, continuously span, so continuously wrap like a surface on them, right? And clearly this is not possible in a continuous fashion, right? It can be, you know, a soap foam or something like that, or like the, you know, the soap bubbles. So you have, you know, like a soap bubble, and then you want to kind of take one line, kind of pass it to another, and pull it like that. So clearly there will be a discontinuity at the origin, because as you approach the origin from here, you get value minus 1/2, and as you approach it from here, from there, you get value plus 1/2. So limit of this f of x, y along this line is not equal to the limit of function of x, y along this line. Therefore, the function is not continuous. Question from Cameron: what does the color changing have to do with the graph? Well, I mean, it's the way where the sort of the curvature of the surface increases, it would add some contrast, right? Sort of so that the colors, the picture would be slightly easier to read. Oh, I'm sorry, I moved it. I don't know how to. I know what to do. We'll just do like this. Like along the graph, the color isn't uniform. Yeah, so that's done for design for better visual effect. Yeah, that's right. It's related to the curvature of the plot. Okay. Any questions? Okay, maybe you can take a small break, and meanwhile you can look at the function. Sort of do the same. I know that you guys have computers and stuff, but try to understand it without doing computers. With the function, you know, f of x, f of x y is equal to xy squared over x squared plus y to the 4. The question is, does it have a limit when x and y go to 0, 0? Is there a limit in this case? Question. So the way to find out if the fraction is continuous is by setting, well, I mean, here, so there is no universal recipe. You have to decide on a case-by-case basis. Here we can see that so the reason why we did it is because there's something interesting going on when x equals to y, right? So the numerator is a quadratic function of x and y. The denominator is a quadratic function of x and y, and they turned out to be proportional exactly for these two choices. Yeah. So try yourself at this new function, the f of xy equals xy squared of x squared plus y to the 4. Can you explain again how we know that the limits are the same when approaching from different directions in this example? Oh, they are not, right? So they will be the same in other points, but so you see, right? So say you only move along this line, right? X equals y, and you approach the origin 0, 0. So this way you approach value 1/2, right? Because if you plug in x equals y in this formula, you'll get 1/2 for all values of x and y, right? So like the restriction of this function on the subset isn't it undefined at 0, 0? Well, you can take the L'Hopital. If you want, you can do so. Yeah. So okay. So let's do this calculation. So you got it right. So yeah. So first of all, I mean, here the L'Hopital is not even needed, right? So you may need L'Hopital in the second example, but here the function is literally a constant, and it just happens to be two different constants depending on different subsets where you restrict where you restrict yourself. Does that clarify the question? Good. So is the other guy, the other function, is it continuous at x equals 0, x equals 0? Again, sort of, you can see what you can first trust you, sort of see what happens. I mean, apply your intuition first, and then just check by calculating what's going on, and then we can plot it. Well, so the question from Sarah: if you do L'Hopital rule, do we differentiate with respect to x or y? So to apply a L'Hopital rule, you need to already pick a direction, right? So say you want to put x equals y or x equals some constant times y. After you've done that, you have a function of one variable, and then you can just apply a L'Hopital rule in the normal setting. I'll be back in 1 second. Okay, what say you? What's going on? You think the function is continuous or not? Let's say x, y. It's not continuous. Which paths, which directions did you choose to establish that fact? Yeah, so let me remove the nodes. Oh, somebody used the, okay, nice idea by Hannah here. So she decided to use parabola, right? So see, if you look from top, it looks like a sort of the sandwich, right? Basically, there's a parabola here, and there's a parabola there, right? So, and then the limits as you do so will be, yeah. So probably this way it will be even faster to establish, right? So if you take this bottom parabola, which would look like what is it, x equals minus y squared, right? Then the function approaches, function is equal to minus 1, right? Minus 1/2. Yes, minus 1/2. And then if you take the top parabola here, then the, I mean, the way I think the place where I drew it is not. Yeah, so yeah, let's look at words, and then when we pick x equals y squared, then the function is equal to plus 1/2. Okay, so there is a discontinuity. Now, let's see what others are doing. So Amok did x equals y, and x equals minus y. So if you do x equals y, you'll get y cubed and half is what is y cubed over y to the 4th plus y squared, right? It's some function that goes to infinity, right? When y goes to what's wrong? Let's see. Oh, so it goes to 0. It goes to 0. Excuse me. Never mind. Right. So I don't think it actually gives you anything, right? So this function approaches 0, and then if you pick x equals minus y, it will still be a function that approaches 0. So when x equals minus y lead you to minus y. Let's cube here. Minus y cubed over y to the 4th plus y squared. So it also approaches 0. So these two lines do not show you much, but these two probably that Hannah chose, they actually do. In fact, you can see here that this line passes through the origin, and this line, oops. And this line passes through the origin. Yeah. But nevertheless, the function is not continuous. Okay. So let's do maybe one more example. Okay, good. So just some of you asking about the connections with sections. So that's section 14.2, which we have completed. So there will be exercises on that. And now let's talk about partial derivatives. Question: if a limit of a function can be approached from infinitely many directions, probabilistically there is going to be somewhere. Yes, good. So of course it's a very strong statement, but because you know what the function actually looks like, you can prove it, right? So what was the definition saying? The definition saying that you're just looking at the absolute value of the distance, right? If you know that the function is continuous, something like polynomial, or okay, let's say so what kind of functions like always continuous, right? So for example, polynomial functions. So Pn of x is equal to x as a vector. Okay, so can you use? No, you cannot use that, right? Because so the questions from Daniel: can you use x equals y minus y to prove that the last function was not continuous? So the last function is not continuous, but you cannot prove it by picking these two directions. If you pick these two directions, that you'll get the same limit. What you should do, you should rather use this parabola that Hannah suggested. Okay, so back to Shala's question. If a function were continuous everywhere from infinite to many directions, how did they not distinguish the function from? Yeah, so if you say we have a polynomial, you know, so x squared plus y squared plus z squared plus xy z, you know, plus xy plus yz. So and then you pick any point, you know, a, b, c, somewhere in R3. So this is a function of three variables, right? What you need to show is that for every point, so you need to show that you know, for sufficiently small delta, for sufficiently small radius, the distance here, you know, x minus a squared plus y minus b squared plus z minus c squared. So if you pick x such that this is less than delta squared, what should happen is that the p of this Pn of x y z minus Pn of a, b, and c is less than epsilon. So for every epsilon bigger than 0. So the fact that we encoded all possible paths, right? So that it's already kind of given here, right? So we're just looking at all the, you know, at the absolute value of the distance, right? So if we can establish that, and for these smooth functions, it's possible to do with some inequalities, right? Then you can prove that it's continuous. So you don't have to manually check all the angles at which you approach the point. Sometimes it's possible that you can literally look at all possible angles in some polar coordinate presentation, but usually it's not necessary. So it's clear that the function is discontinuous, like in previous examples, or it's clear that it is continuous, right? So for example, all polynomials are continuous, right? All rational functions are continuous everywhere except, well, all rational functions are continuous in their domain of definition, right? So if say you have, you know, x plus y plus 2 divided by x minus y minus 1, that is a function f of x, y, right? It's continuous everywhere except the line x minus y equals 1. It's continuous on R2 without the line x minus y minus 1 equals 0. So what other functions are continuous? So it's pretty much all elementary functions that we had. Polynomials, rational functions, exponential functions, logarithmic functions, trigonometric functions, etc. They are continuous in the on their domains. Okay. Shall I just answer your question? So we will do more. We'll do a little bit more investigation for this. In particular, we'll calculate partial derivatives. That's the next topic that we turn next. And there you should be able, when we'll study what happens when you try to differentiate the function. Right. But as far as continuity goes, well, we just need to study it on case-by-case basis. Okay. Other questions? Yeah, so there will be some examples in the homework. We can look at some more examples together if you want. Okay. Good. So now let's talk about partial derivatives. So let's maybe pick some plot. Okay, maybe not as singular as this one. Take maybe, you know, they have plot like this, and so something that is not particularly smooth. And okay. Now the so some of you asked about L'Hopital rule and how to differentiate things. Well, if you have a function of many variables, there are a couple of things that you can do. There's several things that you can do. You can pretty much differentiate the function with respect to any variable, and then by keeping other variables as constants, as parameters. So let's see how this works here. So say, so this is a function. It's a polynomial function of two variables, right? And then here is its plot. It's a nice continuous function. So let's pick a point here, and then we'll cut the plot along the y-axis like this. So this will cut through the graph somehow like that. Right. So we fix a point. So we fix a point with coordinates a and b. So first, let's fix. Let's say b is the a is constant, right? So let's say assume a is constant. Yeah, anyhow, so we would draw the plane. So let's call it plane PA, right? It's a plane in this three-dimensional space that is perpendicular to the x-axis that passes through point A. So in this case, we can write that this is f of. So in other words, we put x equals to a everywhere. So this is f of a comma x, and which is equal to a squared y plus a minus y, which turned out to be a linear function. And so it's y times a squared minus 1 plus a. So which means I need to amend my picture a little bit. So it does look like a piece of line here. And so this graph, if it's cut by vertical planes perpendicular to the x-axis, gives you a bunch of lines with different slopes, right? So the slope depends on where you are on the graph. Okay, so that's first calculation you can do. And second calculation you can do, you can sort of dissect it by a perpendicular plane. So let's write the formula first. So now let's put y is equal to b, and then we calculate f of x comma b, and that will give us b. This will give us a parabola, right? So it's bx squared plus x minus b, which would look like this, right? So we can cut it by this plane, and then here we'll get a parabola whose curvature and shift depend on where you are on the graph, right? And now we can study these functions individually, right? So you can call this function. Oops, what happened? Oh. So we can call this function little f of x. We can call this function g of x. And then we can do calculus for every function, right? So for example, we can differentiate this, right? We can find derivative f prime of x. We'll calculate that. So f prime of one. Sorry, y. It should y. I prime of y. So it's f prime of y. Right, it's a constant with a squared minus 1, which will be the slope of this red line here. And so the tangent of this angle will give you f prime of y at point AB. And similarly, you can study the derivative of the function of the other function, right? So this blue one, so there will be g prime of x, right? Which in this case is equal to, it's a linear function, is 2b x plus 1. Okay. And this is what partial derivatives are, right? So we define, I'll give you the formal definition in a second, but so we'll call these guys the partial derivative. So there's a symbol del f of xy at over dy, right? And this will become the partial derivative df of xy over dx. And here you evaluate the derivative at x equals a, right? And here you evaluate the derivative at y equals b. So the idea behind partial derivatives is that you restrict your function to a function of a single variable by treating other variables as parameters, or as constants, which you do not change, right? You only study what happens. We only study how the function changes as you vary only this one variable, and you do not change any other variables. So let me write it. I'm going to stop sharing now. Any questions while we have those plots? Okay. let's start a new page. Oh, by the way, did anybody try biking on the weekend after knowing how to bike better? So you can improve your performance by 50%. Well, if you haven't tried it, right? So, okay, so here's the formal definition. Okay, so the let me write the definition only for the function of two variables. So let f of xy be a function of two variables where of well, xy, which belong to some domain D, then if the limits if h goes to 0, f of x plus h comma y minus f of f comma y divided by h, and limit as h goes to 0, f of x y plus h minus f of xy divided by h exist, then they're called partial derivatives where this limits exist. Then they are called partial derivatives. With respect to x and y. Right, so this is equal to del f of xy over dx, and this is del, we just call it d, it's a symbol. So in LaTeX, the symbol is partial, backslash partial, and then it's dxy over dy. Yes, it's h. Thank you. That's right. It's same letter as in the limit of function of one variable. Other notations are, you can just write it del x f of xy, or sometimes people just write f prime and x at the bottom. And even the most lazy people, but in fact they're not lazy, they just write it too much, just write fx, right? And it's clear, if it's clear from the context, that already means the derivative with respect to x. Same here, the same as dy of xy. So every notation is acceptable if it does not cause any more confusion. Okay. Well, let's look at some examples. Yeah, so basically, the idea behind it is if you want to calculate the partial derivative, just with respect to the variable x, you treat y as a constant and differentiate it as if y is a constant. And the same is true for the other variable. So, let's say f of xy is equal to sine xy squared plus yx. What's df over dx? What's df over dy? Can you tell me? So first you differentiate, you treat x as a constant, actually y as a constant, when you calculate df over dx. So it will be cosine, let me do the first one, we'll do the second one. So it's cosine xy squared times the derivative of the argument, but here only x is the variable. So it will be like this. What's the derivative of df over dy then? Yeah, that's right. So it's the 2y, the 2xy, yeah, the Hannah did the right calculation, right? So you first differentiate sine, you get cosine, and then it will be well, derivative of the thing inside, which is 2xy plus x. Yeah, that's right. Yeah. So that's that. So and we're talking about geometric meaning, right? So the derivative of the derivative with respect to x shows you the slope of the tangent line to the graph that we drew, right? Which is obtained by intersecting the respective plane with the 3D plot, right? It shows you how fast the function changes in each of the directions. Right? So that's the partial derivative. Yeah. We'll return to meaning to these vectors which go along these directions with slopes of partial derivatives when we'll talk about gradients. Right? We'll do some vector calculus in this for functions of many variables, and we'll use the partial derivatives will determine us. Basically, we'll have a vector. Well, I can maybe tell you right now. So we'll introduce the notion of a gradient. Right, so it's this nabla f, which is, so if f is a function of two variables, then it would look like it's a vector with components df over dx, df over dy. Right, so this will be a vector. And basically, you can see here, the more each component becomes, the stronger is the change of the function in that direction. So basically, this vector shows you the direction of the most rapid change of the function. Right, so if you have, say, a valley or a slope, right? Then this gradient will be the largest on absolute value, where the drop of the height changes the maximum. Okay. How does it differ from the dy over dx is greatest? Well, I mean that was for the function of one variable. Now we have two variables or more variables. So we have to study them together. So that's why the we need to look at derivative in each direction and then make a vector function out of that. Okay. Let's do one more. Now let's talk about high derivatives, higher partial derivatives. So we had partial derivatives, f of x, which is df over dx. Now, and the same, we had f of y, which is df over dy. Again, let's assume that f of xy is just a function of two variables where these derivatives exist, right? Where those limits exist. Now, we can differentiate further, right? So we can define fxx, which is also f xx, the second derivative with respect to s or x, or it's d2 f over dx squared. And so that's one thing you can do. Then you can do fxy, which is f. Let's see, the notation should be, yeah, that's right. So xy, and it's denoted as d2f over dy dx. So so think of it as applying d over dy to df over dx like this. Right, so this is just dx, d over dx applied to df over dx. Then we can do it in the opposite direction, right? We can do fy x, which is f yx in a different order, right? It may be different. We'll see it soon. I hope by now it's clear what's going on. So we take derivatives in a given order, and finally you can do double y. So yeah, we already have 4 different second derivatives of a given function of 2 variables. So if you have functions of n variables, you'll get 2 to the n, right? You can do derivatives in any coordinates, right? So yeah, and then you can ask yourself, well, so because you can already see here that there's an interesting question. Is there any a priori connection between these two? Right, so what happens if you take a derivative over x first and then over y second? Or if you take it in opposite order, and sometimes the answer is the same, sometimes the answer is different. So let's look at an example where they're the same, and look at an example when they're different. So in fact, there's a theorem. Okay, and then we probably should end on that. So there's a theorem which says that suppose that function f is defined on disk on an open disk. And continuous. Open disk, let's call it D. And that f is continuous on D. And if D contains, if point AB belongs to the D, then the second derivatives are the same. Right, so yeah, if a function is continuous, then there'll be no surprises. It doesn't matter which order you take a derivative, xy or yx. And then, but of course, you can. And the counter positive example to the statement will be that if the derivatives are different, if second derivatives are different in both directions, in this x, y, and yx, then the function is discontinuous. So you can check well at home that the examples that we looked at earlier with discontinuous with the different limits as x, y approach 0, they have different. If you evaluate the derivative in x than y, and then in different order, then the answers will be different. Yeah. Okay. So well. So we can check it with this other example here. Very good. So we don't have time to check it. We should stop. So next time we'll continue. We'll talk a bit more about second derivatives and high derivatives, and we'll move on to tangent planes, right? So in one dimension we'll have tangent lines. In 2 dimensions we'll have tangent planes. So we'll describe equations of those tangent planes, and we'll talk about vector calculus and functions of many variables. So no, it's the other way around. So if the function is continuous, then derivatives are equal. There is no opposite statement. So there's a counterpositive statement. If the derivatives are different, that means that the function is not continuous. Okay. The homework will be posted on B courses. Yes, I'll post it in a matter of half an hour. Okay. Other questions? When is the midterm? Midterm is in the end of week 5, so it will be next Thursday. Yes, correct. Next Thursday. So it will be for 2 hours, the entire 2 hours. So think of a midterm as double quiz. Yes, it's a quiz, but only twice longer. Mm-hmm. Yeah. It will be organized in the same way. So maybe 2.5 hours to allow for extra time. Yeah. So, but you should do it within a 24-hour window. So a quiz will be cumulative over chapters 10, 11, 10, 12, 13, 14. Yeah. So it will include the material of the first 4 weeks. Yes. Okay, so if there are no questions, then thanks for coming, and I'll see. Will they be around the same difficulty? Yeah. So literally think of a midterm as quiz times 2, and think of a final as quiz times 3 in terms of workload. Great. See you tomorrow then. Bye.